Oh, can you see my screen now?
Yes, sir.
Okay, so today we'll start inner product space. So as I mentioned in the earlier class, in the last class, that first we will cover inner product space. We will introduce inner product space, and then we will come to eigenvalue, eigenvectors, and diagonalization and other things. Because I might need a few things, a few terminology from inner product space. So this way we'll do it. So let us start. Let us introduce what is inner product space. So we will see what is the motivation behind inner product space, and then we will formally define what is inner product space. So in today's lecture, the plan is to start inner product space. Okay. So let us see why. What is the motivation behind introducing inner product space? So for motivation, you can consider, let's say R2. Let's say consider R2 plane. Then a vector or an element in R2 is of the form, let's say x1, x2, or you can write it as a column vector also. And let's take two vector x and y with the component y1, y2. Okay. You can also write it like x as let's say um, column vector x1, x2, or y as let's say y1, y2. Okay. Then we know the dot product in R2. So the dot product is a well-defined thing in R2, and we can define it as follows: x dot y. If I denote it by this notation x dot y, the dot product in R2, then it is simply x1 y1 plus x2 y2. Right. So now let us look at what are the properties this dot product in R2 satisfies. What are the properties this dot product in R2 satisfy? For example, so let me write down the properties here. So let's say what are the properties this dot product satisfies in R2. So we write this. So properties satisfied by the dot product in R2. So what are the properties it satisfies? So for example, you know that if I take, so you just look at this dot product. If I take the dot product of x with itself, then by definition what it is x1 square plus x2 square, right? And then you can say that this is always, because it's x1 and x2 are real numbers, so it is always greater than 0 if x is not equal to 0. So x dot x, so dot product of x with itself is always greater than 0 when x is not equal to 0. And when the dot product of x with itself is 0, so this is 0 if and only if x1 and x2 both are 0, that means x itself is 0. Right. What is the second property? You can see here by definition, if you take the dot product of x with y, then it is same as the dot product of y with x. So it is also satisfy this symmetry property. Then if you take the sum of two vectors in R2 and then take their dot product with some other element z, then it is equal to x dot z plus y dot z. So it is also satisfy sort of what you can say is that distributive property. And then if I let's say if I take a scalar multiple of any vector x, and if I take the dot product of this with z, then it is same as the same scalar multiplication with the dot product of x and z. Alpha is any scalar. So these properties are one can easily check that these properties are satisfied for the dot product in R2. But what are the information do we get with this dot product, or at least in R2? So what are the information we get from this dot product? So for example, so what information do we get? So we know that if x is any vector, then what is the length? So what is the length of a vector in R2? So length of x. Can you tell me if x is a vector with the component x1 and x2, then what is the length of x?
Distance from origin.
Yeah, but then what is the length? The formula. What is the length?
Under root of x
X2.
square plus x1 square plus x2 square.
Yeah. So it is length of x is simply x1 square plus x2 square uh, square root, right? Or you can say that it is the square root of the dot product of x with itself, right? So let me write this way. So it's the dot product of x with itself. We take the square root of this dot product. So for the length of a vector, I'll use this notation. Later on, I will introduce a different term for this. It will be a norm of a vector or a matrix. But for the time being, for this section or for this chapter, inner product space, I will just use length of a vector. Okay, because for norm, I will independently define what is a norm, and then it will turn out that this length this also satisfy those properties, and therefore we can call this also as a norm. But for the time being, at this point, I will just call this length of x. Okay, and I will use this with this notation. Okay, so this is just the notation for this length. So if we know the dot product in R2, then by using the dot product, we can tell about the length of it. We can measure how big or how small a vector is by looking at its length, and length can be defined by the dot product. What else we can do? We can also tell about the angle between two vectors. So using the dot product, you will see that we can talk about angle between x and y. And this is not difficult to see. So if you just apply uh, the cosine law for a triangle, then you can easily see this. So let me uh, write this here. So if what we have two vectors. So we have y and we have a vector x. Then let's say this is the length of y and this is the length of x. Then this vector is actually x minus y. So this is the length of this vector x minus y. And if suppose theta be the angle between x and y. Okay. So by using this dot product, we can tell about this angle also. Why this is true? Because if you just apply now the cosine law for this triangle with the sides norm x, length of x, length of y, and length of x minus y, then you can easily find this out. For example, let me recall what is the cosine law. Uh,
So
Cosine law
vector
is
vector dot product say
yeah, just a minute. Cosine law. What is cosine law? If we have a, let's say we have a triangle A B C, and with the angle, let's say this is angle A, this is C, and this is angle capital B. So these are the angles between these sides. So then what the cosine law says? It says that you can say that the side C, this side, the square of this, the length of the side C is equal to a square plus b square minus 2ab, and the angle between a and b. So it's cos C. Okay, so this is the cosine law here. Now, if I apply this law here for this triangle, the sides length of x, length of y, then what do we get? So then it would be like x minus y square. Then so this is the length here, and then it is equal to length of x square, length of y square minus 2 times length of x, length of y, cos theta. Theta is the angle between x and y, right? But then you also know, so this is what we have, but then you also know that the length of a vector is actually given by this, right? So if I take the square of this, then it is just x, the dot product of x with itself for any x. So if I apply this for this vector x minus y, then what it is just x minus y dot product with itself. Now if you just apply the product, the properties of the dot product in R2, then you can write this thing here as x dot x minus s2 x dot y plus y dot y. So what is this? This is actually length of x square, length of y square minus 2 times dot product x with y. So now you can see here, you can compare these both sides. So you'll see that these two terms cancel out each other. This 2 is also gone. And then what you are left with uh, is the following. So you can say that it is simply x dot y is equal to length of x, length of y, and cos of theta, cos theta. But then what you can say from here, you can say that cos theta is equal to x dot y, the dot product of x with itself, divided by length of x and length of y. So you can see here that if you are given two vectors x and y, then you can, by using dot product, you can tell about their length. Once you know that length, then you can also tell about the angle, because angle is then just this ratio. So in R2, the dot product tells you the length of a vector. So it gives you a way to say whether a vector is smaller than the other vector or bigger than the vector. So it gives a way to compare two vectors. And it also tells you the angle between any two vectors, right? Now the question is, so this is true in R2 because we know the that this is the dot product is defined in R2, and using this we can tell about these two things: the size of a vector and the angle. But then the question is, can we extend this notion of length and angle to general vector space? Let's say from R2 to R3 or Rn. Then why to strict over only for Rn? Because we know that the elements of a vector space are actually can be treated as a vectors, and for them also we can tell, or this is the question, whether we can say that okay, for these vectors also we can say, we can have this notion of size of a vector or length of a vector, or and angle between two vectors. So the question is, can we extend this notion of length and angle to general vector spaces? So this is the question we want to answer. And the answer is that yes, we can do, provided we have a sort of dot product on that space, or some kind of product that can be used to define length of a vector in that vector space, and also angle between two vectors, by keeping in mind that the dot product is used to define angle and size of a vector. Okay, so what we need, so we need actually a sort of product if you want to extend this idea of measuring a vector or length between two vectors to know the angle between two vectors. So to extend this idea, we need a sort of like let's say some kind of product. You can say it's a scalar product, but then this product should satisfy certain things. These are the minimum things you can expect. For example, you can see here some of the properties. The dot product satisfy in R2. So we can at least expect that the product which we intend to define on that vector space, this also satisfy sort of this kind of properties, because then we can say okay, somehow we can try to extend these ideas to define length of a vector and to talk about angle between two vectors on a general vector space. Okay, so the question here is, can we extend the notion of length and angle to general vector spaces? Okay, so this is what we want to answer. The answer is given by using the inner product. Okay, so here I will define inner product on a vector space over a field F, where F is either R or C. So we will either talk about real vector space, that means the underlying field is real, or complex vector space where the underlying field is the field of complex number. Okay, so let us define uh, an inner product on a vector space. So is there any question at this point? Okay, so let's define inner product then. Yeah.
Sir, how we will means take the angle in Rn, where n will be greater than or equal to 4.
Yes. So this not only I'll answer this question, but I'll answer this question for a general vector space, and the same applies for Rn also.
Okay,
Is it
sir,
okay?
thank you.
So this is, you can see that this is my question, that can we extend the notion of length and angle to general vector space? So we want to extend this idea of like length and angle between two vectors for a general vector space. So it also includes Rn. Okay. So you will see that, okay, at one idea at least you can get from here. So can anybody answer here? Just use the discussion we have made so far. Using this discussion, can you get some idea to define length of a vector and angle between two vectors for, let's say, for R4, or let's say for Rn, for any n? Can you use this kind of idea? I mean, because Rn is still like something in Rn, right? So for example, this
The
dot
length
product
root
is
over of x1 square plus x2 square dot 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 xn.
yes, but what it is? So you know dot product in Rn,
Yes,
just
sir.
like R2 we
Yes,
have,
sir.
you can extend that idea, and then you can say that the length of a vector in Rn is just the square root of the dot product of that vector with itself. It's the same thing, right? You said square root of x1 square plus x2. It's the same thing. But the same way, you can also, once you know the length, then you know some idea here. You can at least define angle between two vectors using this. So if you know the dot product in Rn, then at least you can say that, okay, when I say angle between two vectors, then I mean that this is the angle I'm talking about. Okay? And you will see that in most of our discussion, we will be, in particular, we will be interested for angle or for the notion of perpendicularity or orthogonality. That would be sufficient for us. In most of the cases, we just will focus on the angle where theta is just 90 degree. Then we will see, you can say from here, then that notion can completely be given by using the dot product or the scalar product which we intend to define for a vector space. Then we will say that, okay, if the dot product of x with y is 0, that means they are perpendicular, they are orthogonal, because from here the theta will be 90. So it gives you a way to define angle between two vectors. So the answer of your question is that in this way, you know the dot product on Rn, so you can use this formula, and you can say when you talk about angle, you mean by this. Okay, but not only this, we want to answer this question for a general vector space. And this, as I said, we can answer this by using the inner product. So let me introduce what is an inner product. So let us fix our field. The field is either R or C. So for inner product, I will just use the field as the field of real numbers or the field of complex numbers, and assume that V is a vector space over. Okay. So what is an inner product? So let me define this here. So we just want to extend the idea of this dot product in R2 to a general vector space. Okay. So now let us look at carefully what is this dot product. So this dot product, you can see this is sort of this kind of thing. It's a kind of mapping, you can say. What is dot product? So dot product is a, let's say it's a mapping from R2 cross R2 to R. And what it does, it takes any two vectors, one x and y, and it sends this xy to this x dot y, which is defined by this x1 y1 plus x y2. So it's a mapping, or it's a function from R2 cross R2 to R, such that this function satisfies these properties. So what we will do here, so we will try to define a function on a vector space, or from V cross V to F. F is the field here, such that that function satisfy this kind of properties here. Okay, so let me write this. So why I'm doing it in this way? So that you don't have to remember the definition or the properties satisfied by an inner product. You just recall what dot product in R2 satisfies, and these properties are very easy. So you can simply extend this for a general vector space. So so the definition is given here. So I'm using this notation. This is sort of a standard notation. Therefore, I'm using this notation here. So this is just a notation for a function. You can use any notation like f, g, h, whatever notation you want. You can use for this for inner product. But this is sort of a standard notation, so I'm using this. So this is just a function. This is just a notation. So this is a function from. So this is a function from v cross v to f. Okay, this is a scalar valued function because the codomain is f here. So it's a this is a scalar valued function. Okay, then this function. So it's just a function from v cross v to f. Now this function is called an inner product. It's called an inner product on v if it satisfy these four properties. These four properties are actually motivated, or these properties are actually generalized the properties which are satisfied by dot product in R2. So if you look at carefully, so let me write this property here, and then you compare these properties with the properties satisfied by dot product in R2. So this function from v cross v to f is called an inner product if it satisfies these four properties. The first property is that when you take when you look at this value, the value of this function, so that means you take this x with itself, then it is always greater than equal to 0 for all x in v, and it is 0 if and only if x is 0. So this function should satisfy this first property. This property is called, so this one here, sorry, this one here, this property is called non-negativity, the inner product, and this property is called the positivity. The second one is is that when you take the when you look at this value, the product of x with itself, x with y, then it is same as the product of y with x conjugate. So when I take the bar, that means it's the conjugate. So because this is just a scalar here, and then when I take the bar, so I can talk about its conjugate. So this is the conjugate. So you can say inner product of x with y is same as inner product of y with x conjugate, and this is true for all x y in V. So this property is called as symmetry, conjugate symmetry or symmetry. The third one is that when you take the inner product of x plus y with z, it satisfies this one. Okay. For all, this is true for all x, y, z in V. And similarly, when you do this, then it is equal to alpha times inner product of x with y for all xy in V and alpha in F. So these two properties, these are called linearity in the first component of the inner product. So these two properties are called linearity in the first component of the product. Okay. So if any function from V cross V to F, if it satisfies these four properties, then that function is called an inner product on V. Okay. So okay. So if you compare these four properties, just a minute. If you compare these four properties with the dot product here, then you can see that they are very similar to these properties. For example, here you can see that it's a x dot x. It's very similar to this one, the first one. It's just the notation is different. Otherwise, you can see this dot product on R2 satisfy all these four properties. Therefore, it is an inner product. Okay. So only thing is that here you can see here in R2 is xy is same as dot product of xi is same as dot product of yx. So it is the conjugate is because it's a real number, so it's conjugate is same. Here we need the conjugate. Okay. Now if so, let me just fix this terminology. So let me just introduce this thing also. A complex or real vector space with an inner product. So when I use this abbreviation I dot p dot, I mean inner product. So with an inner product is called an inner product space. Okay. So vector space together with an inner product is called an inner product space, and I may use this abbreviation for this I dot p dot as well. Now, if you have an inner product on a vector space, then you can talk about length of a vector. So you can define length of a vector. So this is the notation I'm using. So this is length of a vector. So length of V is actually defined by taking the square root of the dot product or the inner product of V with itself. And you can also talk about angle between two vectors. So angle between two vectors, let's say U and V in V. So how it defined? It is defined by this ratio. You take the inner product of U V and divide by the product of their lengths. Okay. So now you can see here, you with this notion of inner product or with this with the introduction of inner product on a vector space, you can talk about length of a vector this way, and you can also talk about angle between two vectors. Okay. So we can using the inner product, we can extend the idea of length and angle into vectors for the geometry space. If we can define an product, we can talk about length and angle between the vectors. And as I mentioned earlier, in particular, we will be more focused on the vectors. So when I talk about angle, so we will be more focused or interested on, in particular, the angle of 90 degree, or you can say that when we have this notion of orthogonality or perpendicularity of two vectors. Yeah, so you had some question. Yeah.
सर फर्स्ट पॉइंट में सेकंड पार्ट पॉजिटिविटी क्यों बोलता है उसे?
So it's like when x is not 0, then it is always positive. Okay, so when
Okay,
x
sir.
is not 0, then it is always positive, and it is 0 if this dot product is 0, if and only if x is 0. So if x is not 0, then this is always positive. This scalar is always greater than 0.
Okay, sir.
Sir,
Okay. Yes.
sir, when we define a vector space on the field of complex number, then sir, that inner product will be also in terms of real number when we are taking that.
No. So here you see, I did not mention real and complex. The only thing is that for the first property, you need that the dot product of x or the inner product of x with itself should be real. This is where I am comparing, because you, for this you need a ordered field. So x dot x should be a real number, then only you can say whether it's greater than 0 or less than 0. For complex numbers, we cannot talk about this order, right? So this quantity here, this quantity should be real, the only thing. Otherwise here I did not mention anything. Okay, so this f can be any field. It's maybe r, it's maybe real, it's maybe c. The only thing is that the first property should satisfy, and the first property, when I say x dot x is greater than equal to 0, the inner product of x with itself is greater than equal to 0, that means it has to be real. Then only you can talk about this. Is it okay?
Sir, can you take one example which is on complex field and there?
Yeah. I'll take. Don't worry. I'll give examples of inner product.
Okay, thank you, sir.
Is it okay? Yeah, I'll give. So it's just the definition. So far we have just talked about the definition. I haven't given you any example of inner product, but you will see that some of the examples you already know. Some of the examples of inner product you already know, and they will satisfy the properties of inner product, and therefore you can call those function as inner product on a particular space. But before I proceed, let me make some observation here. I'll give you examples, don't worry. So today in today's class, the point is to introduce inner product and to make you comfortable with this new term. So observation is that if you just ask, okay, sir, why do we need this conjugate symmetry here? Because the other properties, if you come the first property, they are simply
Sir, your voice is breaking.
Yes, sir, voice is speaking.
Yes.
the extension of the
So you're not audible.
properties which are satisfied by the dot product. If you look at here,
Sir,
the
sir, your voice is not clear, sir.
properties here.
Yes.
So inner product, there the dot uh, uh, can you hear me now?
Yes, sir.
Yes, sir.
Okay. I'm sorry. There was it was a network issue. So uh, let me see whether can you see my screen? Is it shared?
No, sir.
Not yet. Can you see it now?
Yes, sir.
Okay. Okay, so let us continue our discussion. So I was saying that you can see that the three properties here in the definition of the inner product, these three properties, the first, third, and fourth, these properties are simply taken from the dot product in R2. But the second property here, we have something different. We need conjugate symmetry here instead of just symmetry. The reason here is that I'm also considering the field here, the field of complex number, and for this I need this, because otherwise I mean I will never be able to define a function that satisfies this thing. So what I'm saying is the following, that in this observation you can say, or let me write this as a question here, that why do we need conjugate symmetry in the second point here? This is the question. Or you can say, can we say that, or does there exist a function g from v cross v to c? V is a vector space over S over C. So can we define a function g? So it's like a sort of similar function. So the question is, can we define a function from v cross v to c such that it satisfy uh, these three properties? These three properties, first, third, and fourth, and also the second property, but just symmetry without conjugate symmetry. Can we define such a function? So this is the question. So what I'm saying is that if I just remove this conjugate symmetry and I just consider the symmetry here, can I define such a function when v is a vector space over C? This is the question. And the answer is that no. If we drop this conjugate symmetry here, and instead of conjugate symmetry, I just take the symmetry here, then I may not be able to define such a function when vector space is over the field of complex number. Okay, so why do we need this? This you can see by this observation that if I take any vector, so if I take, let's say, x, any non-zero vector not equal to 0 in V, where V is a vector space over C, so V is a vector space over C. So the question is that, can I define such a function when V is a vector space over C? So can I define a function, let's say G, from V cross V to C, such that this function G satisfy these three properties, first, third, and fourth, and the second property it satisfy just with the symmetry, not the conjugate symmetry. That means I'll just drop this thing here, remove the bar. Can I define such a function? Answer is that you cannot define such a function. Reason is that if I take any non-zero vector x here, then by first property, let's say, let us call this function g, then the function then this, or let me just use the same notation here. So if I take any x not equal to 0 in V, then by the first property, it is 0 because x is not equal to 0, so it is always greater than 0. Now since here field is the field of complex number and x is a non-zero number, so since x is not is a non-zero vector, then this I times x, I is a scalar in C, so ix is also non-zero because I is non-zero, x is non-zero, so it's a non-zero vector again. Since it's a non-zero vector, this should also be non-zero by using the first property of the inner product, so this is always greater than 0. But then if you use the third and fourth property, so for example, the fourth property says, so if I use the fourth property, what it says? It says that alpha times x inner product with y is alpha times inner product of x with y. So if I use this, then it would be x inner product of ix, right? But then I use the symmetry. So then the symmetry says that it is same as ix times x. So what I'm saying is that if I remove the conjugate here, just instead of conjugate symmetry, if I just take the symmetry, then I get some kind of contradiction. So here I'm using the symmetry only, not the conjugate symmetry. And then again I use the fourth property, then it would be I square inner product of x with itself. But then I square, we know the value of I square is -1. So it would be minus x, right? So now we have some kind of contradiction that you see this x inner product of x with itself is greater than 0, but then with the minus also we are saying this is greater than 0, so it is not possible. So it's a contradiction. So we cannot define a function from V cross V to C that satisfy these four properties where the second property is replaced by just symmetry. So let me write conjugate symmetry so that you remember this instead of just symmetry. Okay, so we cannot define such a function, so we need conjugate symmetry in the second property. Also, you can make this observation, the second one. So let us call this first one. The second observation is that you can simply observe that if I look at this value of this inner product, that means inner product of x with alpha times y plus z, where alpha is a scalar and x, y, z, they are vectors in V. Then you can easily show that this is same as alpha bar times inner product of x with y plus inner product of x with z. Why this is true? Because you look at here, this follows from the third and fourth properties of the inner product. Why this is true? Because of the second property, you can see that this is true as alpha y plus z. This is equal to alpha y plus z inner product with x bar. But then this is also equal to alpha y, or I can write it as y x, the alpha times y x plus inner product of z with the x bar, right? It's just I'm using the third property here, third and fourth property together, and then this is same as alpha times y inner product with x bar plus z x bar, because these are just two complex numbers and I'm taking the bar of their sum, so it is same as this. But then this is equal to, again this is equal to alpha bar yx bar plus inner product of z x bar, right? But then
Sir,
what it is, yes,
ओके सर, अब जब डबल बार लेंगे तो फिर वो सिंगल लाइक एक्स वाई हो जाएगा, फिर से सिमेट्री यूज करेंगे.
yeah, so now you take again this is xy plus xz, right? But then this is what we wanted to show, that this is same as this one. So it's just I'm using the properties of inner product. So let us look at some examples of inner product. So now we have like at least clear idea of what is an inner product and some basic knowledge of how to use these properties with this observation. Let us look at some examples. So before this, let me ask you, have you studied this inner product before also in your graduation?
No, sir.
Yes, sir.
No, sir.
No,
Some of you, okay, I
No, sir.
understand. Okay, fine. Anyway, I'm teaching you the way, like you have not seen it before, but anyway, it's those who have learned this earlier, it would be a sort of revision for them, or you can like recall your learning. Anyway, so let us look at some examples. So I will just give you these functions. So inner product is just a function from V cross V2 to the field that satisfies certain properties. Now, when you say that a function is an inner product, so or when I ask whether a given function is an inner product, what you have to do, you just see that it is a well-defined function from V cross V to F, and it satisfies the four properties. If it satisfies all the four properties, then you say it is an inner product on that vector space. Otherwise, it is not. So if it is violating any of these four properties, then you say that it is not an inner product. So here I will not prove whether a given function is an inner product or not, but I'll just give you example, and you can explore these functions, or you can check that whether these functions satisfy these four properties or not. Okay, so let us take V as Rn over R. Okay, so V is the vector space where V is just Rn, and what we need to define an inner product, we need to define a function from V cross V to R here, Rn cross Rn to R, right? So that means if I take, so let's say the vectors are denoted by this one, any two vectors, you can take this one, and then how you map these functions. So you need a function, right? Rn cross Rn to R. This is what you need. So any function that satisfies these four properties would be an inner product. So you can define this function. So this is the notation if I use, then you can say that you take this xy, which is denoted by this one, then this is just the dot product. That means xi, yi, I equal to 1 to n. So this is the dot product on Rn, and you can see that this dot product satisfy all the four properties of the inner product. It's a well-defined thing. It's a well-defined function from V cross V to R, and it satisfies all the four properties of an inner product, and therefore it is an inner product. So this function defines an inner product on Rn. Okay, and this inner product, so you have to verify this. Okay, I'm not going to verify these 4 properties because these are like simple calculation. You just have to verify these 4 properties, whether these functions satisfy all the 4 properties or not. So I'm saying that it is an inner product, that means it satisfies all the 4 properties, and this inner product has a name. You can call it, or we will call it, as standard inner product on Rn. Okay, so whenever I say that you consider standard inner product on Rn, I mean by this. All right, so this is an example. Now you can see that this way, since we can define an inner product on Rn, you can talk about length of a vector and angle between 2 vectors by using this inner product on Rn. All right. Similarly, you can define an inner product on Cn also. So like the same way, if I take x and y 2 vectors, now this time these components are coming from C. So if I take x and y 2 vectors in Cn, then the function you define by using this xi yi bar I equal to 1 to n. So it's sort of dot product on Cn, but we have the we have to take the conjugate of the second component. Why do we need this? Because if we don't take the conjugate of yi for each I, then it won't satisfy the second property of the inner product. So we need this thing, and you can verify that this is again an inner product. This is an inner product on Cn, and this inner product is called as standard inner product on Cn. Standard inner product on Cn. All right. So now on Rn you have an inner product, on Cn also you have an inner product. Now let us talk about matrices. Okay, so Rn Cn tak to sab sahi tha. So now let us move to other vector space. For example, space of functions, space of matrices. Can we talk about angle between, because the elements of vector space are called vectors. So whether this vector space is a space of matrices, if it is a space of matrices, then the matrices or the elements of this vector space, which are matrices, they can be treated as vectors. So again, we can talk about their length of a matrix, or angle between 2 matrices. Similarly, if the vector space is the space of functions, the same question we can ask, whether we can talk about length of a function or angle between 2 functions, because they can be treated as vectors. So let us consider the space of matrices first. So let us suppose that V is the vector space of n cross n matrices over the field F. Okay, and then how we define this function? You just define this function from V cross V to F by using that trace of the product A B star, where star is the complex conjugate transpose of a matrix. Okay, I hope that you know this notation. So this is the function I'm talking about. You take 2 matrices A and B and define this product by using the trace of the product AB star. This function again it's a well-defined thing, and it actually defines an inner product on this n cross n space of n cross n matrices over there. Okay, so this B star here, let me write. This is the complex conjugate transpose of B. Okay, so in other words, how can you define this? And if you let's say if A is denoted by let's say Aij and B is denoted by Bij, then this inner product of A with B, which is trace of AB star, this what it is? It is this thing. I equal to 1 to n, j equal to 1 to n, Aij, Bji bar. Okay, this function again you can verify. You can verify this by using the properties of trace. This is again not difficult. You can just use the properties of trace of matrices, trace of a matrix. Just use the properties of trace, and then you can verify that this function satisfy the four properties of an inner product, and therefore this defines an inner product on this space. This inner product we call as an standard inner product on the space of n cross n matrices. Okay, so we call this as a standard inner product on space of n cross n matrices over there. All right, so you have to verify for all these examples. You have to verify whether they actually define inner product on the given space. Okay, this will also make you comfortable on checking whether a given function is an inner product or not. Okay, so you just verify this. Let me give you a few more examples. So we have talked about Rn, Cn, and space of matrices. So let's talk about space of functions. So let us consider V as let's say this space of continuous functions on closed interval AB. So it can be a complex valued functions. It can be a real valued function. So let us consider this V. So this is a space of continuous functions from closed interval AB to F. This is a vector space. In fact, it is an infinite dimensional vector space. So the other three examples I gave, they are all finite dimensional vector space. But here, this example is also an example of an infinite dimensional inner product space, infinite dimensional vector space on which we will define now inner product. So if you take how we define this, if you take two function f and g, and then you send this or you define this product by this definite integral ft gt bar. So this is the product dt. Okay. Now here you may ask, why do you need this continuous function? Why not for other functions? So you have to verify this. You need to see that if I drop this continuity assumption, then it may not be a function. It may not be an inner product. I'll give you some detail here, some idea why. But let's say that we want to check whether this is an inner product or not. Okay, it is an inner product as I'm saying, but you need to use continuity here. Otherwise, if you drop the assumption, or if you instead of continuous function, you just take a space of functions from AB to F, then the same function may not be defined, may not define an inner product. Okay. So let us check. Whether this is an inner product or not. Okay. So let me check this for you. Let me check whether this function defines an inner product on this V or not. So let us check this. So you can check that this is a well-defined. So well-defined thing. So that well-definedness you can check. This is a well-defined function from V cross V to F. V is here this one. Now we have to check whether it is an inner product or not. To check that it is an inner product, we have to check the four properties of an inner product, right? Now you can verify that the last three properties, they are very straightforward to check. They follows by using the properties of an integral. So for example, if you look at the second property, f dot g, inner product of f g, so that means the conjugate symmetry, this easily follows, right? You can verify that this is very easy to check, that this is equal to this. So this you can verify. It's very easy by just manipulating, by doing some calculation here, simple calculation. You can, or simplification, you can do this. Similarly, the third property, what is this? Alpha plus g h is equal to This is also straightforward to check by using the properties of the integer. The fourth property is also easy to check. This is again by using the properties of an integer. So these three properties are fine. What about the first property? So let us check whether the first property is true or not. So for first property, the first property has two components, non-negativity and the positivity. The non-negativity is also very clear here. So for example, if I take the inner product of, or if I look at this value here, the product of f with itself by using this this function or this definition of this function, what it is integral from a to b ft bar dt, but then this is a b mod of ft square dt. So mod of ft is a non-negative function. So value of the integral, can you say that this is always greater than equal to 0?
Yes, sir.
Yes, sir,
Right?
by Rima.
Yeah, so this is fine. So this is also, the non-negativity is also fine. But now how about the positivity? So for positivity, what you have to see, you have to check. So now to check that this is 0 if and only if f is 0. Right? So if and only, both ways. So one way is true, that if f is 0, if the function itself is 0, then clearly, so you can look at here, when you do this, then it is actually this one. So when the function value is 0 or the function itself is 0, then this integral is always 0. So this is again fine. Right? Now, can you say the other side also? Can you say that if this is 0, then this is also 0? This is the question.
Continuous
Yes,
while
sir.
no.
If f is continuous.
This is, in general, this is not true. Why this is not true? Can you give me example of a function for which uh, this is 0? That means what is this? So this is this one. This is 0. So can you define a function from closed interval a b to f for which this is 0, this integral is 0, but the function itself is not 0?
Sir, x minus 1 to 1.
X minus
1 to 1.
x
मतलब
minus 1
f
to 1.
नहीं मतलब कि
Sir,
f
fx
equals to
to
x
x. Yes.
or minus
Huh?
1 to 1
And
interval.
Minus 1 to 1. So this is one example. So x, the function itself is not 0, but this is 0. You can also take, like, you can say, okay, the function, some simple example also. So this is also fine. So for example, you can take ft is, let's say, 1 if x is equal to, let's say,
constant
1 by
function.
2. Yeah, x is equal to 1 and x is 1 by 2, and it's 0 if x is not equal to 1 by 2, and you define this function from 0 1 to, let's say, r f or whatever. So this function is a non-zero function. Clearly it has a value. So what is this function? This function has, at this point, it has a value 1, otherwise it is 0. So you can see that the area covered by its graph is actually 0. Its graph and the real axis is 0. So this is clearly, this is not true for a general function, but if f is continuous, then you can ensure that this happens. When this happens, then it implies that f has to be 0. Okay, so why this is true? So let us prove now this other side. Suppose that this f, product of f with itself is 0. And we have to prove that this implies that f is 0. Okay, now suppose that f is not 0. Now can you give me some idea why this is true? Some idea? So what I'm saying is the following. So this is true, this is also true, but for this, because I'm giving you the reasoning here, because let's say this is 0, and using this we have to prove that f is 0. So suppose that so let this is 0, but f is not equal to 0. F is not equal to 0 means there exists some element t naught, let's say in the closed interval AB, such that f t naught is not equal to 0. The function is not 0 means at some point its value is not 0. But since now f is a continuous function and this function is non-zero at a point, this implies that there exists an interval, let's say delta greater than 0, such that this function is not 0 for all such that this function is not 0, or let's say, sorry, this is t, not t naught. So there exists an interval such that, or you can say there exists delta greater than 0 such that ft is not equal to 0 for all t in this delta neighborhood of t. So that means for all t in this interval, because f is continuous. But now if f is not equal to 0 in this interval, then what you can say? Then this implies that if you look at this now, what is this? This is this thing. Right? And this thing is always greater than equal to t naught minus delta to t naught plus delta, and then mod ft square dt. But since ft is non-zero in this interval, so then the value of this integral is greater than 0. But then this is a contradiction that that ff is 0. I mean the product of f with itself is 0. So this is a contradiction, and therefore we can say that this function actually defines an inner product. So this is how you have to check for all these, for whatever function you want to say that this is an inner product. You just need to check these 4 properties, and once you are convinced that these 4 properties are satisfied, then you can say that that function defines an inner product. All right. So let me give you one more example. So
Sir, I have a
if
question.
you, yes.
सर जो मैंने एग्जांपल दिया था वो काउंटर नहीं कर रहा था इस चीज को, बट वो मतलब फॉरवर्ड डायरेक्शन में काउंटर कर रहा था, क्योंकि वहां पे ff0 हो रहा है बट f0 नहीं है।
ff
मतलब इनर प्रोडक्ट ff0 हो रहा है, जैसे हमने f को x लिया और -1 to 1, देन f0 हो रहा है बट f0 नहीं है, fx है।
यस सो
तो वो इस चीज को काउंटर कर रहा है ना, ff0 इंप्लाई नहीं कर रहा है कि f0 है।
So you need to see now what you are defining, that is a that's an inner product or not on that.
So
Okay, so you just, what I'm saying, you just look at your f, that function, your interval, and then you talk about this. Okay.
So I'm clear about
So
it. Sir,
yeah. So you just what you are saying is that the function fx. Okay, so maybe then, so if you have this, then you just fix a and b, which are in the like in the one side of the plane. Okay. So you just verify if it is like not satisfied, then you just change the interval. So it should be like so you gave this example fx equal to x from -1 to 1.
yes, sir.
Right. So this function is, this integral is 0, but the function is not 0. This is what you are saying, right?
Yes, sir.
Yes. So then that's I agree. So you just change this. So let me just fix this here. Okay. Is it okay now?
Yes, sir. Now, okay.
Yeah, that's a good observation here. So I should have written this thing. So now I think it's fine.
So one more thing.
Yeah.
सर लास्ट जो आपने कंट्राडिक्शन लिखा हुआ है ना, उसके पहले जो इंटरवल है वो आई गेस कि वो ओपन होना चाहिए, टी नोड माइनस डेल्टा, टी नोड प्लस डेल्टा.
It's fine. So if it's let's say it is open, then you take a delta which is smaller than that. You can always choose delta greater than 0 such that you can talk about this closed interval. So for example, let's say what I'm saying is that if you have, let's say, t node here where the function is not 0, then you will say that there exists a delta such that in this neighborhood delta node minus delta, delta node plus delta, this is non-zero. But instead of that, what I'm saying, you just take smaller than, so you choose a new delta which is smaller than this delta, then you can talk about this closed interval and you call this as delta. So you can always say that there exists delta.
Yes,
Is
clear
it
now.
okay?
Actually, yes, sir. Okay, sir. Actually, most of the time उनका open interval रहता है ना, that's why I asked.
Yeah. So there exists delta, so you can always choose in this
Yes, sir.
way.
Clear. Thank you, sir.
Okay. So let me give you one more example. So if I just fixed any matrix, let's say Q over F, and let's say this matrix is invertible, then you can verify that this function from Fn to Fn cross Fn to F, which is defined by this way, y star q star qx. Okay, so y star y is a vector. You can treat x and y as column vectors, and then you can talk about this matrix vector product multiplication. So this is a well-defined thing, and you can verify that this also defines an inner product on Fn. So now you see you have two kinds of inner product on Fn. One I have already given on Rn and Cn, the standard inner product. But then I have also given a way to define inner product on Fn. So there, if you change the matrix Q here, any invertible matrix you take of size n cross n, and then you look at this function, this defines an inner product. So by this, you can define actually infinitely many inner products on Fn. So what I'm saying is that there is actually a way to define arbitrary inner product. So far we have seen some examples, but depending on what you want from your inner product, in some cases you can actually define the inner product. So let me give you this as an exercise, but this exercise is very useful. This gives you a way to define arbitrary inner product. Like you remember while learning this linear transformation, we saw one result that gives us the way to define inner product. Like if fix some n vectors in, you choose a basis for the domain, and then you look at so assume that it's a finite dimension thing, and then in the codomain you fix n vectors, and then there is a unique map that that has this fbi equal to wi kind of thing. Okay, so there is a way to define, and then in particular, if suppose we want something extra from this linear transformation, for example, we want say null space of this transformation should satisfy something, or the range space should satisfy something, then depending on that we will just uh, assign these or choose these vectors in the codomain accordingly, or we choose a basis of the domain accordingly, right? So there is a way to define linear transformation from one vector space to another vector space depending on what we want. Similarly, for the inner product also, we have a way to define arbitrary inner product on a vector space. So let me give you this as this result as an exercise. So this is an easy exercise to verify, but it's very important. As I'm telling you that I may ask you, okay, define an inner product on a vector space that satisfies certain thing, and then you have to use this exercise. This is one possibility is that you just guess something, okay, कि ऐसा हो जाएगा शायद. But or you just use this exercise, that this will guarantee you that your vector space or your inner product will satisfy what you want if you use this result properly. So I can write this here, a way to let's say define arbitrary inner products on a vector space. So what this result says, so if suppose we have two vector space, let's say V and W over the same field F, okay, and let us suppose that we know an inner product on W. We know, so you assume that you know an inner product on W. So I am using this notation. The subscript W means this is an inner product on W. So let this be an inner product on W. So we are given two vector space V and W, and we know that we know at least one inner product on W. Okay, so we know an inner product on W. Okay, or we are given an inner product on W. Now let T be a linear transformation from V to W, which is linear and invertible. So this T is a linear transformation. So the linear transformation which is also invertible. Okay, so we have three things. We have V and W to vector space. We are given an inner product on W, and we also have a linear transformation from V to W which is invertible. Okay, then using this hypothesis, these three things, if you look at this function which I'm using by I'm using this notation, P subscript T UV, how it is defined, it is T of U, T of V, and this is inner product on W. Now if you look at this function, so this function is a function from V cross V to F, because W and V both are over the same field F. So this new function, so let's say this rho T, this is a function from V cross V to F. Let me write it again. So then this function, then the function rho subscript T. So this subscript T is used just to mention that this is the transformation I'm using from V cross V to F, defined by this rule that you take any U and V and you assign this to this T of U, T of V inner product, and this is the inner product in W, because T image of U and image of V, they are in under T, they are in W. So you can talk about this quantity here in the right hand side. So this is an inner product in W. But then if you look at this map rho T, then this is a well defined thing, and this actually defines an inner product on V. So what this result says, so you have to verify this is an exercise. So this is true, this is the result. What you have to do, you just have to check that this function, this satisfies the four properties of an inner product. Okay, if you just have to verify that. This you can verify using the fact that this is an inner product, and this transformation is linear and also invertible. Okay, so this defines an inner product on V. Now using this, you can see that if you know an inner product on W, then using this inner product on W, you can actually define an inner product on V. So this gives you a way to define an inner product on V. Now you see, if you change the inner product on W, or you change or you take any other linear transformation which is invertible, then you will get a different inner product on V. Okay, so this result gives you a way to define arbitrary inner product on a vector space. So let me give you one example to use how to use this one. For example, let us see let us define an inner product on the same space. Let's say whatever we have talked about so far. this one. Okay, so this is the space C close 0, 1. This is the space of all continuous function from close interval 0, 1 to F. Okay, F is either R or C. Okay, so this is the space, and we want to, so maybe I should not write it in this way. So let's say our V is C01 is the space of continuous function from 0, 1, close interval 0, 1 to R or F. So let's say F. And we already know an inner product on V, right? Let's say we want to define another inner product on V. So we already know one inner product, that is this one, right? This one. And let's say we want to define another inner product on this. This I can do by using the above result. So what I have to do for that? So I need to choose W. So W I can take as V itself, right? If I want to use this result, then I need an inner product on W. So I already know one inner product on this space. So that is this one. So I can take this inner product on W. So what it is this one. So this is now I have. Third thing, I need a linear invertible map. So if I take in particular this map, you can take any linear invertible map. So let me take this one. So what it is? So if you take any function here, ft here, you send it to tft. Okay. Now you can see that this is a linear transformation, and it is not only linear, it is also invertible. So this you can verify. This you can verify. So now we have we have W with an inner product, and we also have a linear invertible map. Okay. Then by using this result, the above result, we can find an inner product. So then the above result says that this function, what it is like 0 to 1. So if you look at this one, what it is, T of U, inner product of T of U and T of V. So what it would be? It would be T of Ft and T of Gt bar dt, right? But then what it is 0 to 1 T square Ft Gt bar. Okay, so it's actually more T square Ft Gt bar dt, right? Now this is an inner product. This is an inner product on C01. Now you don't have to prove that this is an inner product, because you are actually using this result. So from this result, if you have proved this result, then you don't have to prove that this is an inner product, because actually it follows because of this result that whatever function you have defined, this is an inner product. But if you want to use this result, you have to ensure that all the hypotheses of this result are satisfied. For example, you have an inner product, you have a linear transformation from V to W. W is V here, and then this linear transformation should be linear and invertible. So everything is fine here, and therefore this function here, this defines an inner product. So you have another inner product on this V. So this way you can just change the transformation, and you can define an inner product on a given vector space. All right. So this way, so how much time do I have? I just got 4 or 5 minutes. So let me give you then one more example for this.
So
Let's say, yes.
सर ये जो linear transformation define करा ये infinite dimensional पे ही invertible होगा क्या? Finite dimensional पे?
Yes, yeah, it will be. No. So here I have not assumed anything on the dimension. You see here, if everywhere, if anywhere I need anything, I will just mention. So here I did not mention anything. So it is actually true. It's a 1-1 and onto transformation.
सर ऑन टू कैसे कर सकते हैं? ऑन टू में हमें इशू लग रहा है.
You just verify. Okay, just do some calculation.
Okay sir.
Okay, so this is a linear and invertible. Oh, just a minute. So it's a linear and it's a okay. So it should be non-singular. So just a minute.
Yes sir.
It should be, yeah. Just a minute. So it should be just null space of T should be 0. Yeah, for this transformation, I think you just need the non-singularity. That means you don't need ontoness here. Yes, you are right. So actually, yeah, you just verify this result. Actually, you just need the non-singularity. That means the if it is invertible, of course, then it is true. So the
Yes,
result is fine here. If it is invertible, it is fine. But it is actually using an extra condition here. So basically you just need the non-singularity. That means the oneness. The null space of this linear transformation should be 0. That's all. So then I think I should modify this here. So I haven't proved this. So you just verify and you see if you like you need invertibility or just the thing that null space of T or the oneness. So just see this by proving this null space of T should be 0. Okay, so you just replace this condition by null space of T equal to 0 after verifying this, and then I think it is true.
Okay.
So why do we need the invertibility? So let me just explain this. Why do we need this invertibility? We need this invertibility just for the first condition of the inner product, right? Because this should be right. So this should be 0. So for invertibility, we need or not invertibility we need for the first condition here. So I think other things are fine. The only thing is here. So for this positivity, I think you just need that null space should be 0. So I think with that it is fine. So okay, so I think that should be enough. So you just assume that null space of T is 0. So if it is so I know why this has happened, but this is a good observation. You just made this clear here, because I saw this result in Hoffman and Kunj, and in Hoffman and Kunz, they assume that the vector spaces are actually finite dimensional, and then therefore in finite dimension, this invertibility oneness is same as ontoness, and therefore they just wrote invertible. So I took this result from Hoffman and Kunz, and they probably have assumed that these vector spaces are finite. But you are right that actually we don't need invertibility. We just need the fact that null space of this is 0. Is it fine now?
Yes sir.
Okay. Yeah, I understand why this has happened, because I took this result from Hoffman and Kunj, this exercise, and I think they have assumed, and I missed that assumption. So you just use that null of T is just 0. You just verify. So there are situations where I may miss some points. So you just point these out, and things are clear to everyone. I think we are done with the time. So you can try to define like whatever inner product I have given you so far, some examples. You can use these inner products to define other inner products on a given vector space. Okay, and as I mentioned, and as one of you pointed out, you just verify that what things you need. So when V and W are infinite dimension, do you need invertibility or just the fact that null space of T is 0? And this is what I think that you just need for the positive, for the positivity, for the first property, you just need the fact that null of T is the zero space. That should be enough. Okay, so we can stop here now. And if you have any doubt, any other doubt, you can ask.
So we will verify. Actually,
Yeah, you just
next.
verify, explore, read the book, see some more examples, and then things would be more clear. I hope that you have understood the definition. We will continue developing on this inner product in the next lecture, and I will also upload a tutorial sheet based on whatever we have covered in last two lectures, and for the upcoming next lecture. Okay, so we can stop here. Thank you. Bye bye.
Thank you, sir.
Thank you, sir.